Hello guys, my name is Mahuana Mlatleki. I'm a mechatronics engineer, and at the moment my role, I work for PCS Global as a design engineer in an electrical department. Today I'll be talking to you about Sasol Techno X, which is a career exhibition. I'll be talking to you about a day in a mechatronics engineering's life, whereby I would say mechatronics engineering is just, in terms of literature, it's an integration of electrical, mechanical, and as well as programming. However, I would say that is a bookish definition that I already knew coming from high school, transitioning into university in terms of what I wanted to pursue. Graduating, I didn't definitely have an understanding, or it was a little bit more complicated than the literature writings. So I would say mechatronics is a plethora of interests in IoTs, big data analysis, industrial automation. You have a lot of factories whereby you're controlling those with control systems. So in the end goal is to achieve smart factories where machinery talks to each other, as well as for the management role, be able to interpret that data into proper decision makings. Well, in mechatronics, I would say with my role sitting in design, obviously, I have to sit down with more like liaising with the client in terms of specifications of whatever may be the case where the client wants to automate a process. So basically with those specifications from process engineers, you get what you call PNID diagrams. These are process and instrumentation diagrams with equipment listing on it, pipings, you have valves, and you have a little bit of your instrumentations, for example, flow sensors. You also have pressure sensors. You also have, in terms of, you would have as well as pressure indicator transmitter or pressure indicator controllers, as well as your pumps. So it basically shows the more like a piping scenario of the process. But in overall, you have all these equipment there. One, as a mechatronics engineer, you should be able to interpret and read your PNIDs. So in that, it actually gives you an idea of what the process is and how it is actually running and how every equipment is laid out in the field. But remember, now you are working on this from a design perspective. Therefore, from a PNID, you allocate your instruments which are out there in the field. From that, you're now working on what you call an IO list. So your IO list, it's inputs and outputs of that process. And how you transition into that, then after allocating, let's say for example, you're looking at a flow transmitter or a level indicator transmitter, you have to actually know what type of an input is this. In terms of inputs and outputs, you are talking digital inputs, you're also talking digital outputs, analog inputs, analog outputs. So basically, you're just taking all your instruments there in the field on a PNID diagram. You are actually saying, allocating your IO list with some tags, because your PNID also comes with tags and tag names. So you allocating that, okay, this instrument and LIT, which is a level indicator transmitter, is actually your analog input, because you are actually from a field measuring a level of maybe a fluid or so. So from there, you're actually getting readings. So it's analog because it's going to be transmitting some values to you, which in the background are scaled in terms of from 0% to 100, maybe ranging depending on the instrument, whether it's a current or a voltage instrument, whereby it's 4 milliamps to 20 milliamps or 0 to 10 volts. But before we get into that, you just have to actually decide on the inputs, allocate them correctly, because at the end of the day, your end goal is to actually have a complete idea as well as a vision of what instruments you need, how many are they, and how they actually operate. So that I would say that's more of it of a PNID diagram, and how it actually links from the process guys to the design people now who are going to be automating the process. So now you have your PNID and you've done your IO list, and you actually know how many digital inputs you have, how many digital outputs or analog inputs and outputs that your system requires. So you are now moving to an electrical side of things to actually now have a general arrangement to say, okay, now I am having this much of IOs, these are digitals. Now you have to actually also look into different brands. We have different brands in terms of PLC controls, which is a programmable logic controller that is mostly used in industrial applications. So this PLC has cards on it, which are digital, which are also analog. So they can be either be digital inputs, digital outputs, analog outputs, and analog inputs. So based on the number of IOs you have, now you look into your PLC and cards and you say, okay, let's take a hypothetical situation where let's say we are having 20 digital inputs for this process. Now, if you are having 20 digital inputs and then maybe you're looking into a Siemens products and you're going with a PLC in Siemens, you might find that most of the cards have like 16 digital inputs. So it means that at the end of the day, you are going to have 16 digital inputs on that card, but there's still a remaining 4, which now makes up the 20 that you have. Now those other ones need to move on to the next card. Therefore, it means that for 20 digital inputs, you're requiring an amount of 2 digital input cards. Then this now boils down to an electrical schematics. Now you are making a general arrangement of a control panel. So a good control panel consists of the power section, control section, which is your PLC or the many industrial computers that you might have to control the process, and then it also has your IOs, now your outputs and inputs, which are now linked to your field instruments. Now from your field instruments, you are now communicating directly to the PLC. Maybe you have the sensor switching on some process which now sends that as an input into the PLC. But now remember, you're only working with design at the moment, not the philosophy and how the process is running. You are still trying to figure out the amount of the equipment that you actually need, boiling down to we are actually just building a bill of materials. So from this process, when you have allocated your cards and you know how many cards and how many you need for each IOs you have, you now come up to a general arrangement of your control panel. Like I said, a control panel has all those sections: your power section, your control, and your field, which is your IOs. Then you actually lay it out in there. It actually gives you an idea of how big is my panel, my enclosure, and my mounting plate, because now it also gives you an idea of what trunkings you got, DIN rails, because you need trunkings for running the wires, but you also need DIN rails to mount your equipment on. So you are having a GA, you are more having like an idea of where everything will be laid out in a control panel. You are having your PNID, you've actually from it made your IO list, as well as you've now moved on to the electrical side, which is your GA. Now you have an idea of equipment that you will need from the power section, from the control, which is the PLC and the cards, as well as some networking devices there, but then you're also having an idea of terminals that you will need and relays that you are actually needing in your process. In terms of materials, now you are building up to a BOQ, or rather known as a bill of quantity or bill of material, which is a BOM. Now you now putting all this together in terms of listing what I need, what is this and what is that, what equipment I am having. For an example, this is the PLC that I'm having. It has this part number. I need this many cards. These are the part number of these cards. So this overall BOQ is going to help you to procure, to get all that equipment to help you started in building and wiring the control panel. You actually now have your BOQ or your BOM, and you send it out to procurement. Remember, in an industry now, you're working with departments, you have people who are going to buy the material for you, but here you are in a design space, in a design department. So what good is a GA? I mean, at the end of the day, these components, all of them need power, and they need also signals, which are your inputs and outputs. They need to be receiving signals or sending out signals. Therefore, you carry on. Now you've allocated where your GA, your general arrangement of components is, but now you need to give these components power and signals. Now we move on to another section in electrical design, which is now called multi-line schematics. In the multi-line schematics, you are basically wiring all the components, you are giving them power, and you are taking from your PL control side, you are taking from your card, you are taking wiring from there to the terminal point where you are going to be wiring your inputs or outputs, as well as to your relays. Basically your digitals, you would want to have them fused and protected in wiring them running to terminals. But for your digital outputs, you are also looking into running them into relays first, and then back to the terminals. There's a little bit of a reason behind that, which some of the equipment that you're having from an output point of view, why would you be using relays? Mainly because you're having components, your outputs there, which you want to be switching, which have much more rating of current or voltage than the one that is being given out by your digital output cards. Therefore, you kind of like giving the signal to switch on your relay coil, and then give out from the coil, give out the amount of power that is needed to power that particular instrument. Let's say maybe you are powering a valve, or maybe another instrument that requires a little bit more of power to actuate it and have motion going, because remember, at the end of the day, you are automating a process. Therefore, there are valves involved that you are opening and closing. You're also having motors running and switching on and off. Therefore, it also boils down to how much of a current rating and voltage they require. So in short terms, multi-line schematics, you are now wiring up in terms of design what is wired from your power section. From the power section, you're looking how much is my customer providing me in terms of a power source. Now, where does my power source go into my panel? From my panel, how am I distributing it to the rest of these components? Therefore, it is actually a process that keeps running. Therefore, you just wiring from there in terms of your breakers, your incomers, and then from there you're distributing to a power supply. You're saying my control needs 24 volts, then it's more like a converter. So from maybe you're giving it to 30 volts, your power supply, then it gives out a 24 volt DC. Now you're taking this 24 volt DC to your PLC and your cards, and then to the instruments as well. So that is much more of it, or in terms of your multi-line schematics. With the experience that I have received in the field, I've worked on various fields. I've been exposed to much industries. Like I say, mechatronics is broad. At the end of the day, you have to specialize in something. I love design because it gives me that adrenaline rush whereby at the end of the day you are having your plant, but it came from just specifications and rating of your components and directly to building. So mechatronics, like I said, you have your electrical, you have your mechanical, as well as your programming side. It gives you that feasibility to specialize in something. My end goal is to actually become an industrial automation specialist. So at this moment, I am in a design environment, but yes, I do program PLCs and processes, as well as other IoT devices. But it has given me an exposure in fields of water treatment. It has given me an exposure in mining. It has given me exposure in food and beverages, as well as many more. I've actually worked on pneumatics as well, which is another means of control in terms of air, and hydraulics in terms of control using air, your oil. So the experience that I've had is really amazing, but this does not end in you doing the role. You actually have to give in the hours, put in the works, because industrial automation is forever changing. It is a big deal. It is what is the future you want to have. When the future gets there, because of the fourth industrial revolution, you want to be doing a very, very fascinating course. If I get bored of design now, it's easy for me with mechatronics to switch to control systems and get to program PLCs and other stuff, or instrumentation. So it gives you a broader perspective in terms of the industry, as well as their exposure that is there in very, very various industrial fields.